in this article, we prove a number of theorems, but the most well-known is a proof that the Weeks manifold is the hyperbolic three-manifold of minimum volume. So I'm going to have to explain a few terms. For example, what's a three-manifold? And then what does it mean for it to be hyperbolic? And then what is the volume? So let me start with what a three-manifold is. A three-manifold is a three-dimensional object, but there are certain constraints. So for example, I suppose I'm a three-dimensional object, but I wouldn't qualify because I have a boundary. My skin is essentially a two-dimensional boundary. There's another sort of bad example. You might take like this baseball. It's three-dimensional, but it doesn't really qualify for our rules because it has a two-dimensional boundary, which is, well, basically the cover of it is a two-dimensional boundary for it. And there's stuff inside, which is three-dimensional, but that still doesn't adhere to the rule because we want to have no boundary. So we require that our three-dimensional objects have no boundary. Now, another restriction is we also want them to be basically finite. We don't want them to be infinite in extent. Now, as you think about it, it's a little hard to understand what a three-dimensional manifold, something that adheres to this criterion is. So the one about not having a boundary. So as another example, we have a little cube here. It's also three-dimensional, but again, it has the boundary which causes trouble. And as you can see, it's got a top face and a bottom face, faces on the sides, and a front face and a back face. What we'd like to do, if we want to construct a three-dimensional manifold, i.e. a three-dimensional object with no boundary, we'd like to somehow get rid of these boundary pieces. And one way to do that would be if we could somehow maybe glue the top one to the bottom one, and glue the side to the side, and this one to this one. And if we could do that, we could get rid of these boundary objects, which we want to do. Well, that's hard to visualize because how do you glue this side to this side, and how do you do this one? I mean, even if this thing were made out of rubber and you could sort of move it around, you'd still have difficulty doing that. Well, confronted with this problem, we can sort of, it's useful to gear down a dimension and look at a simpler problem. And the simpler problem being, how about a two-dimensional manifold? Well, the same thing happens. So let's take a look at this sheet of paper, which is two-dimensional. But again, it has this problem that it has a boundary on it. So it's got this top edge and bottom edge and right edge and left edge. And it's more or less the two-dimensional analog of the cube because it's, well, if it were a square, it would be the two-dimensional analog of the cube. But it's a rectangle, so it's pretty close. So now the question is, can we eliminate these boundaries by maybe gluing the top to the bottom and the side to the side? And the answer is we actually can. And if you do the first gluing of the top to the bottom, you can see that you've eliminated this boundary over here. And so it's now a cylinder. The problem, though, is that you have a boundary here, a one-dimensional boundary here, and you have a one-dimensional boundary here. So now we have to get rid of those. Well, if it was made out of rubber, I could do that. I could sort of start bending it around and get this one over to here and get rid of that boundary. And if I did that, if I had the rubber, well, then I would end up with what is known as a torus, but it's also an inner tube or maybe a donut. And so here's a donut. As you can see, it's got the hole in the middle. And the donut, of course, this didn't quite work. You have to look at the surface of the donut, because I'm trying to give you an example of a two-dimensional manifold. And it's the surface of this thing that qualifies as the two-dimensional manifold that you get by taking the sheet of paper and gluing the top to the bottom and the side to the side and so on. Right. So that's the surface, which is the boundary of that donut, is a two-dimensional manifold, and it was gotten from the paper. Now, as you can imagine, you could do the same thing with the three-dimensional cube, except the trouble is you have to sort of go into the fourth dimension to do all the gluing and so on. But it can be done. So three-dimensional manifolds are going to be sort of analogs of that construction that I gave. Of course, there are others as well, many others. Now, so that's a three-dimensional manifold. What does it mean for it to be hyperbolic? Hyperbolic geometry is a geometry, the non-Euclidean geometry, discovered by Bolyai, Gauss, and Lobachevsky about 200 years ago. And it sort of revolutionized mathematics and, in some ways, thought. And this geometry differs from Euclidean geometry in various ways. For example, in Euclidean geometry, if you have a triangle, the angle sum is 180 degrees. In hyperbolic geometry, a triangle has angle sum less than 180 degrees. So there are clear sort of differences. Nonetheless, what we're assuming is that we're looking at three-dimensional manifolds which admit a hyperbolic geometry. That is, you can measure things. You can do geometry. You can measure things, and the measurements adhere to the rules of hyperbolic geometry. So we've got a hyperbolic three-manifold. You can do all these measurements, and they're nice sort of measurements. And then the question is, what do we mean by the volume? Well, the volume is the size of the manifold. And the size is just gotten by using the hyperbolic geometry to do your measurements, and you can measure the size of your whole space, and you get some number, and that's the volume of the manifold. So if you look at all three-dimensional manifolds that have hyperbolic sort of geometric structures, you can look at all their volumes, and the claim is there's one which is smallest. And we proved that a certain manifold called the Weeks manifold is the hyperbolic three-manifold that has the minimum volume. And so that's the most well-known theorem in this paper. And I suppose there's a question as to why that's interesting. I mean, it's one thing just to state what's going on, but in addition, just sort of the question as to why should we be interested in this particular question. So maybe I'll try to explain that by starting out by discussing how I got interested in the problem in the first place. So I was a graduate student at Princeton in the late 70s. And while I was there, Bill Thurston was revolutionizing the theory of three-dimensional manifolds. So when you look at three-dimensional manifolds, it's difficult to understand them. I mean, partly because of this visualization problem where you have to go to maybe the fourth or the fifth dimension to sort of carry out a process of making it. And it was a subject that it was difficult to really get good results. Now, it was known, however, that if a three-manifold admitted a nice geometric structure, then you could use the nice geometric structure to try to understand the three-manifold more powerfully, because you could use the geometry to help you understand things. Thurston's remarkable insight and hard work put forth the notion that in many, many cases, the three-dimensional manifold admits a good geometric structure. So then that revolutionized the theory of how geometry, or how the theory of three-manifolds should be studied. In particular, he made this big conjecture which said that any three-manifold can be cut up in a natural way into pieces, each of which admits a good geometric structure. So this introduced geometry in a very powerful way to the theory of three-manifolds. Now, in addition, Thurston found that when you start looking at three-manifolds and try to put geometric structures on them, it turns out that hyperbolic geometric structures are the ones that keep on cropping up. And his claim, which he proved in many cases, was that really the most important and abundant and the most interesting class of three-dimensional manifolds are the hyperbolic three-dimensional manifolds, the ones that admit these non-Euclidean sorts of geometries discovered by Bolyai, Gauss, and Lobachevsky. So if you're interested in three-dimensional manifolds, and that's an interesting subject with a lot of motivations, historical and natural. I mean, for example, just trying to understand what the three-dimensional universe is, that would be an interesting question. If you're interested in three-dimensional manifolds, and I think you should be, then you're almost led inexorably to wanting to know about hyperbolic three-dimensional manifolds, because they're the big class, the big important class within three-dimensional manifolds. Right, and so I was a graduate student at Princeton when this was all going on, and I was interested in geometry, so I started reading up on trying to study this and understand it, and naturally I wanted to think about an open problem that would be interesting, and one problem that came up was the one that finally we ended up solving in this paper, the one about the volumes. So let me just mention that when you're trying to understand a hyperbolic three-manifold, what's the first thing you might do to try to understand it? Well, I think if you lived there, if you lived in this three-dimensional manifold, you'd probably be, maybe the first thing you do is start measuring things, because you've got the means of measuring things. So let's just start measure the whole space. Just try to measure the size of the whole space. And if you do that, you find out what the volume is. Well, Thurston proved that among the class of all hyperbolic three-manifolds, well, he proved a very interesting structure theory about the possible volumes that can occur. But one thing he proved was that there exists a least volume. And there's some finite number of manifolds that he claimed that there would be a finite number of manifolds that realize this least volume. And so then people started wondering, well, if we want to understand hyperbolic three-dimensional manifolds, at the very least we should be able to find the one which has the minimum volume. It seems like a very natural question to ask, and so I started thinking about that. And early on, I had some success, and I was able to find a lower bound for the volume of hyperbolic three-manifolds. So I was able to prove that all hyperbolic three-manifolds have to have volume bigger than 0.00069. And my method was to show that in the manifold, if you had a short geodesic, a closed-up loop, a geodesic is basically something which is straight in the metric, and if it somehow comes back on itself and it's short, then you could put a big tube around it. And this big tube, the shorter the geodesic, the bigger the tube provides a certain amount of volume. And so playing around with these ideas, I could find objects in the manifold which provided a certain amount of volume, and lo and behold, when I sort of worked everything out, the bound was 0.00069. Now, on the other hand, mathematicians started thinking about what would be the best candidates for these low-volume manifolds. And they came up with various examples, and eventually they stabilized on one, which was the smallest that they found, and they couldn't find any smaller for however long they were working on it. And so that was sort of the leading candidate. And it was independently discovered by Jeff Weeks and by Matveev-Fomenko. And it's obtained by 5152 Dane surgery on the Whitehead link in the three-sphere. But the construction is not so important. It's just they found some manifold. And the volume of this manifold was roughly 0.94. So the game was sort of underway of trying to show that this manifold really had the lowest volume, and we wanted to get 0.94, and so far we knew that at the very least we knew that the lowest volume one had to have volume at least 0.00069. So there was a pretty long gap to go, and that was a problem that I had done some work on it, and I continued to work on it, but that was 30 years ago, or 29 years before we ended up getting our proof. So there was a long process of working on it. There was this gap of the Weeks manifold had volume about 0.94, and the lower bound that I had gotten was 0.00069. So there's a big gap there. And with a certain amount of work, I was able to improve this a little, and some other mathematicians as well. And we got it up to 0.001. Which isn't much of an improvement. Well, it's maybe a 40% improvement or something, some little improvement, let's say. And on the other hand, there was a big gap here. And so I think people didn't really have a good idea about what to do. And so I worked on other things, and other people working on other things, and we just, I studied other invariants and other subjects. But then in the 90s, I started working with Dave Gabai and Nathaniel Thurston. And we were working on a different problem, one about finding out whether homotopy hyperbolic three-manifolds were actually hyperbolic. So that was the question. And Dave Gabai had done some very good work on that, and he realized that he needed some other people to sort of bring on board in this project. And In particular, in trying to prove this, we needed to understand solid tubes around these short geodesics in hyperbolic three-manifolds. So again, a geodesic is like a straight is something which is straight within the metric, but it somehow being it's going to be a geodesic loop, it's going to come back on itself. And the idea is we studied the shortest geodesic in the manifold, and we used we needed to get pretty big tubes around it. I mean, that's what we needed to be able to implement some of Dave's theorems and prove the big theorem we wanted to prove. So we set out to work on that, and we had some ideas, and we realized that we were going to need to use a computer. And in particular, we somehow changed the whole problem into analyzing a six-dimensional parameter space. And we had to analyze this space and break it up into little boxes and analyze different pieces of the boxes, and we actually had to end up having to break it up into like a billion boxes and analyze these billion boxes. But we had a big advantage on our side in that in our group was Nathaniel Thurston, who is a brilliant programmer, just brilliant. And he was able to help us with, well, he wrote this great program. And we were able to succeed at this venture. And in addition, we got such big tubes around these shortest geodesics that we were able to greatly improve the lower bounds for volume. Instead of the volume bound being like 0.001, we had gotten it up to 0.1. So we had made a 100-fold improvement, basically. And so now things started looking sort of promising that maybe we could get all the way up to 0.94 roughly and show that the Weeks manifold was the hyperbolic three-manifold of minimum volume. There's still a gap. It was 0.1 to 0.94-ish, but it certainly was a lot better than being at 0.001. And so a number of mathematicians started thinking carefully about this project now, because we had used some new ideas, and then Dave Gabai and Peter Milley and I had come up with another idea which we implemented, which sort of showed a route towards thinking about it some more. And a bunch of mathematicians, Andrew Jaworski and Fred Gehring and Gavin Martin, and worked on it as well. And the bound started going upward until it was 0.335. And in particular, there was one piece of work by Ian Agel, which was particularly nice, I thought. And Agel's approach was to look at these low-volume manifolds. Agel's approach was basically to look at these manifolds which have, let's say, a short geodesic. And if you look at them, if you somehow perturb them and sort of distort them a little so that these geodesics shrink, well, if you make them shrink more and more, and you're actually changing the manifold, but if you sort of make the geodesic shrink more and more, as we knew, or as I had proven before, they have these big tubes around them. So they start drifting away from the heart of the manifold, and then in the limit, the thing goes off to infinity, and you're left with what is known as a cusp. So you're led naturally to studying cusp hyperbolic three-manifolds. And the idea is that Agel showed how you could sort of control the volume of one of your original manifolds by comparing it to the cusp manifold and getting some, and he had formulas for doing this, which were quite technical to derive. But it was a very nice relationship showing that you could understand the manifolds you wanted to understand by looking at these limiting objects, these cusp manifolds. And cusp manifolds are a lot easier to deal with because I got a cusp there. In fact, as it had turned out, I had studied cusp hyperbolic three-manifolds earlier, and I had worked with Chris Chow, and we had actually found the lowest volume cusp hyperbolic three-manifolds, and we had seen that their volumes, the lowest volume cusp manifold was like 2.02988, and you could sort of couple that with Agel's result, and then you got Agel's good bound of roughly 0.3 for all hyperbolic three-manifolds, not just the cusp ones. And so that was a very attractive sort of theorem that he had. Now, another thing that was going on in the world of three-manifolds is that Thurston's geometrization conjecture, which I had mentioned before, which said basically you can cut a three-manifold up into you can naturally cut up a three-manifold into pieces which admit good geometric structures. That was proven by Perelman in his celebrated proof. Brilliant. And so it's just a great and powerful result. And I think that Perelman's approach is very sort of hands-on, where he really did it in such a way that I think people could really use the tools. In particular, it turns out that Ian Agel, and Nathan Dunfield realized that they could use Perelman's approach to strengthen Ian's original theorem. And they were able to get the volume bound up to about 0.66. So now it's up to 0.66, and you want to get it up to 0.94, or at least that's what you think you're going to try to do. I mean, people have been trying to find lower volume manifolds in the weak manifold for a long time, and they hadn't succeeded. So you sort of guessed that that was going to be the winner. And so far, you've got this lower bound up to about 0.66. And so we realized, Dave Gabai and Peter Milley, and Peter Milley, Dave Gabai, and I realized that we had a way of analyzing hyperbolic three-manifolds, which was really quite new and had some very good potential, and that if you sort of coupled it with this result, there was a real chance of getting it. In particular, our approach sort of worked both with standard three-manifolds and also with these cusp manifolds. And we had been spending, we decided to focus on the cusp manifolds, because if we could get a really good cusp manifold result, then we could couple it with the Agel-Dunfield approach, and maybe get the full result. And so we worked on this, and one of the little problems that sort of confronted us was that you're not really going to win. You're not likely to win if you just keep on pushing up your bound all the time. Somehow you got to hit the nail on the head. It's not enough just to say, well, this is I got a little bit bigger lower bound, a little bit bigger lower bound, a little bit bigger lower bound. Somewhere you're going to have to show that this one, the manifold, that this is the minimum volume one. So we had to come up with a way of doing this. And what we basically did is in our analysis of these cusp manifolds, we realized that in a very specific way, we were able to show that either a cusp manifold was topologically complicated or it wasn't. Now, if it was topologically complicated, then if it was topologically complicated, then there was a lot going on in there, and we can get a lot of volume, and so we got pretty good volume bounds in that case, and we were happy with that situation. In the case where it was sort of topologically simple, we understood precisely what we meant by topologically simple, and with some excellent computer analysis by Peter Milley, we were able to completely analyze all of these cases. And so we looked at these cases over here, and we knew what all the manifolds were. We just sort of basically had a list of all the manifolds. And so the situation then became, on the one hand, if it's complicated, topologically complicated, you get a lot of volume, and then you're basically, you're done. And if it's not topologically complicated, then we had a whole list. And so we just sort of, Peter Milley started analyzing this list, and he was able to determine that, lo and behold, we understood the lowest volume, like basically the 6 lowest volume cusp manifolds, and then you could apply the Agel-Dunfield result, and you saw that the Weeks manifold result dropped out, that we had found the lowest volume hyperbolic three-manifold in general. And so that was the result in the paper. And the paper, of course, went into all this stuff about the dichotomy between the topologically complicated and topologically uncomplicated, and the classification of all these things, and so on. So that was the culmination. The research process is, in this whole venture was pretty amazing. I mean, the whole venture took 30 years, 29 years, I suppose, technically. And I mean, when I started out, I think I had this notion that mathematical research, I wanted to do it sort of on my own. And so the early results I had, it was basically a matter of, you sit down with paper and pencil, and you try to analyze all these things. And, I got some decent results and all that. But it also became apparent over time that I'm very good at certain sorts of analysis and not so good at other sorts of analysis. And I know certain things very, very well, and other things I don't know so well. And it turned out that I was finding that collaboration was just a fantastic tool, and especially if you work with people like Dave Gabai, who's just a topological wizard, and Nathaniel Thurston, who's a brilliant programmer and just a tremendously insightful mathematician, and then Peter Milley. Well, Peter, he was working with Dave and I, and he really knew the topology, he knew the geometry, and he could tie it all together with the computer analysis. And so there was this great interactive process where we'd sort of go back and forth and get all ideas, and it really was a great opportunity. Now, also in this process, there were so many different strands of work coming in from the past and from the most recent sorts of things. And I mean, the library is so important in this sort of venture where you've just got to have access to all of this work, old results, new results. And now, of course, it's great because you can do things online and you get the library's access to all these journals, and it's just, it's almost unbelievable, actually, when I get to use this stuff. But, I have many fond memories of, research excursions in the library, and one of them on this project involved, I had this idea that you can improve volume results by using sphere packing arguments. And what I needed were sphere packing results in a hyperbolic space. And so I didn't know what they were, and so I just started trying to track them down. And they were sort of obscure because they were all done. It turns out that they were mostly done by a Hungarian school of mathematics, and so somehow you have to find these things, and I'd find an article, and then I'd have to go over, it referred to another article, and then there was another article, and it was really quite a fun venture. So that's some of the aspects. There was another thing that early on when I started working with Dave, there was another fun aspect, was that it was hard to find time in what was the teaching schedule and all of that to do really uninterrupted work. And so we decided that we were going to start working early. And so what I would do is I'd get up at 4 o'clock in the morning, and then at 4:30 I'd drive over. I was at USC at the time, a visitor, and Dave was at Caltech, and I'd drive over to Caltech, and at 5 o'clock, we'd be set in an office, and we'd take a nice big classroom in Caltech, and we'd just get to work. And then we'd work on, and and the thing was, we'd take some breaks and try to refresh ourselves. And when 11 o'clock rolled around, we had done a fantastic amount of work, and we were all done. And it was sort of that was a nice aspect as well.
Okay, and finally, a chance to inspire young mathematicians. What inspired you to become a mathematician?
So how did I become a mathematician? Well, when I was young, I was very good at math. So 6 years old, 7 years old, 8 years old, that probably amounted to being good at adding and subtracting and doing things like that, or doing calculations. And so it was always what I seemed to do best, and it always seemed sort of natural. At the time, though, I didn't have any understanding that you could become a mathematician. I mean, well, not that a 10-year-old should know what your profession could be, but I sort of thought that I would become an electrical engineer. And the reason, of course, is that my father was an electrical engineer. My father worked at Bell Labs at the time, which is a very great research institute there. And when he was working at Bell Labs, he and other people there realized that to do their work properly, they needed to know more mathematics. So they started teaching themselves mathematics. And I know my father gave some lectures on the things he was reading, and other people gave lectures on things they were reading. And eventually, he decided that he wanted to get a PhD in math. So he started taking courses at Rutgers, which was the local university. And after a while, he liked it more and more, and he eventually got his PhD in math. And so then I realized that you could go on and get a PhD in math, and I mean, I sort of realized a little more what the possible jobs were in mathematics, but I realized that it was a viable sort of career option. And also then I had a tremendous resource in that, he knew all sorts of math, and so if ever I had a question, I could always ask him. Another odd sort of, another thing which helped me, I think, along the way was that when I was around, I think it was 8th or 9th grade, I got into something called the Columbia University Science Honors Program, which met on Saturday mornings at Columbia. And I lived in New Jersey, and so I'd have to take the bus to the Port Authority and then take the subway up to Columbia and sit in on some class. And I always tried to take the most mathematical ones that I could, but it was really a little more science-oriented. So yeah, there was a little bit of a tension there. But one time, for example, they had a course on algebraic topology. And in contrast to my experience at middle school and high school, where I pretty much understood everything pretty quickly, here it was really tough. I mean, all the students were, really very, very strong, and I think the professor, had sort of grandiose notions about what he might be able to teach us. We didn't really have the background for it, and he was struggling with trying to find out, what level to pitch it at. And I don't think he had a lot of experience at teaching this sort of class. And one other problem was there was one student in the class who really knew the stuff well, and he'd always be piping up, go on, go fast. He'd just say, yeah, we know this. And so the professor moved at a rather quick pace, and I got the experience that you couldn't expect to always understand what was going on in a math class. You might sit there and you'd learn a few things and other things you didn't know, but if you took down notes, then you could go over it. And I will admit that I had the nice resource that I could go to my father and say, hey, we did this stuff and I didn't understand it, and he'd explain things to me. So we had a lot of sessions where he explained what was going on. So this experience of trying, a math class at the Columbia University Science Honors Program and struggling, it was not, I accepted that. I mean, that's how it was in mathematics. You don't expect to understand everything quickly. You just have to work hard. You have to be prepared, and you have to, you got to work on the stuff afterwards as well. And so when I was an undergraduate at Brown, I happened to be there at the time when it was sort of the golden age for undergraduate mathematics at Brown, and there were so many good math students. And so the experience of struggling with math and having to work hard on it and go over your notes time and again, and that helped me succeed. And so and then I guess even as an undergraduate, I always tried to keep open the possibility of I might go into something else. But the math worked out, and I continued.